So now we're going to start talking about functional groups. Now, the thing is, we've been talking about alkanes, and while they're great and they're useful, they really don't do all that much. And so what we do is we add some other elements into these organic compounds or change something about the connectivity of the atoms. And when we do, we change their properties, we change their reactivity. So now, if we have, say, a double bond, it can undergo a reaction to form a bigger molecule or to do a variety of different things. So what we're going to do in this section is actually explore what these different functional groups are. And we're not going to worry about naming these yet. We haven't gotten there yet. We will look at some names of them later on. Right now, you just want to be able to identify these functional groups. And so we've seen alkanes at this point. We're familiar with those. And we're going to go on first to look at alkenes and alkynes, and then look at some other functional groups and kind of how they pair up and how we can tell the differences between them. So the ones you need to know are the ones that are listed here. If you notice, there are a few more in the picture than you actually need to know. Specifically, we're not looking at alkyl halides right now, thiols, the amides, or the amines. We're not worrying about. I'm mainly worrying about the ones that have multiple bonds or oxygens in them. We will see a couple of other ones later on, and we'll talk about those as we get to them. But for right now, we're going to focus on these 10 of them. Now, alkane really doesn't have a lot of functionality. We group it here because we're comparing it to alkenes and alkynes, but it's technically not an actual functional group. It's more there for comparison. The first one we want to look at are alkenes. And when we have an alkene, we have at least one double bond. So one carbon-carbon double bond. It can have more, but it has to have at least one. And so when you go to the grocery store and buy bananas or tomatoes, a lot of times those fruits were not picked ripe, but people are more likely to buy bananas that are already ripened, that are already yellow, or the tomatoes that are red. And so they actually use ethene exposure to get these to kind of hurry along the ripening of their skin. So they haven't developed the full flavor that they would from ripening on the tree or the vine, but they will have the appearance that they are fully ripened, and so they actually sell better in the store. And that's not going to hurt you. It's merely an exposure to the skin. It just starts a reaction in the skin to get the color to change. But that's what they use, is an alkene. We see other alkenes in a lot of different types of compounds: beta-carotene in carrots, pinene, which is found in, not surprisingly, pine trees, and limonene in lemons. And you notice if we look at the beta-carotene up here at the top, you notice that there are actually many double bonds in here. And it doesn't matter whether there's a lot of double bonds or whether there's just one double bond. We still group all of those together by calling them alkenes. So anytime we have at least one double bond, we're going to call that molecule an alkene. Now remember, with the alkenes, we always saw that ANE ending. Now when we're dealing with alkenes, we're going to see the ENE ending. So that's a sign that we're dealing with something that has a double bond. So the third part of that, we had alkenes with all single bonds, alkene with a double bond, and alkynes have a triple bond. So if you've ever seen an acetylene torch, what you're actually looking at is ethyne, and we have a triple bond there. So anytime anything is an alkyne, it has a triple bond, and we use the ending YNE to represent that it's an alkyne. Now, there are compounds out there that have double and triple bonds, or that have multiple functional groups. We're not going to worry about those. We're going to worry about identifying individual functional groups within a molecule. Once we start adding multiple functional groups, the nomenclature gets a lot more complicated. Knowing what's the more important functionality and what's the lesser in functionality, there's actually a rankings list. So don't worry about having to distinguish a molecule that has both a double bond and a triple bond. We'll just say, yes, it's got an alkene, it's got an alkyne, and we're done with that. We're not going to worry about naming that. And that's true regardless. We will talk about nomenclature as we go through the course, but that's one thing that we won't do, is explore nomenclature when there are many functional groups, especially unless it's for like a special class of compounds like carbohydrates, which kind of have their own nomenclature system because of their unique characteristics. So to kind of summarize what we looked at, and we saw this picture in class the other day, we can talk about hydrocarbons, which just means that things have hydrogen and carbon. And we're going to talk about the other functional groups here in just a few minutes. But first we want to go back through our hydrocarbons, and we're looking at saturated versus unsaturated. And remember that saturated means that we have the max number of hydrogen atoms. So we have all single bonds because we have as many spots as possible taken up by hydrogen atoms. When we look at unsaturated, which we look at for alkenes and alkynes, we see that we don't have the maximum number of hydrogen atoms. So if I look at the structures of a molecule with a double bond or a triple bond, I see that if I took away that double or triple bond, I could actually put more hydrogens into the molecule. So those are, as a group, known as the unsaturated compounds. Now there's a third kind of group called aromatic that kind of looks like an alkene, and in one sense it is an alkene because it has a double bond, but because of the way the bonds are arranged, it's actually kind of a special class all its own. And what we notice is that we have 3 alternating double bonds, and we're only going to look at this in a 6-membered ring. We can have other molecules that have an aromatic structure, but this is the one we're worried about. And specifically, we look a lot at benzene as our example, where we have these alternating double bonds. It's 6 carbons in our ring with 3 double bonds in that, and that's known as an aromatic. So that's the kind of structure we're looking for, and sometimes we represent this a little bit differently. Instead of drawing in the 3 double bonds, we'll actually draw it with a circle in the middle, just to represent that those bonds are kind of even all the way around, that those electrons and those double bonds are distributed around the molecule. But for your purposes, know that these both mean exactly the same thing, and either of them just represents a benzene structure. So we've looked at alkanes, alkenes, alkynes, and aromatics that are only dealing with carbon and hydrogen atoms. Now we want to look at some molecules and some functional groups that have oxygen in them. And there's going to be 6 of these, and I've put them in pairs of 2 because there's similarities in the structures between each pair that I'm going to show you together. And I'm going to point out the differences between them so that when you're identifying functional groups, it makes it a little bit easier to decide which one you're actually looking at. The first pair we're going to look at is alcohol versus ether. And when we look at an alcohol, the characteristic that makes it an alcohol is the presence of this OH group. Now in this example, the OH is on the end of the molecule. We can also have an OH attached anywhere in the chain of that molecule, and it's still an alcohol. So what we're looking for is that OH group, and that's the defining characteristic that makes this actually an alcohol. We notice that when we look at the ends of these, we're always going to see this OL ending. So we have ethanol, methanol. That OL ending indicates that we're dealing with an alcohol. For an ether, which is very similar to an alcohol, and it doesn't appear that way at first, but what we see is that we have a chain of carbon atoms in our alcohol, we have an oxygen and then a hydrogen attached. For an ether, we have a chain of carbon atoms, we have an oxygen, but instead of having a hydrogen here at the end, what we have actually is a carbon or a carbon group. And it can be any number of carbon atoms, but remember the end of a line represents a carbon, so we've replaced that hydrogen with a carbon. And I can have a lot of different variations on the ether as well. I can have different numbers of carbons on each side of my oxygen. So lots of different ways to arrange it, but the distinguishing thing is the presence of the O carbon bond, the oxygen carbon bond, rather than the oxygen hydrogen bond that we see here in alcohols. So alcohols and ethers kind of look alike. Alcohols have the OH group. Ethers will have an O group attached to an R group. And when we talk about an R group, what we just mean is some chain of carbon atoms. It doesn't matter whether it's 1 or 10 or 20, it's just a chain of carbon atoms. Now we're going to look at aldehydes and ketones, and what we're going to look at are the differences in these, and it's going to be similar to what we saw with the alcohols and the ethers. First, we want to look at the key characteristic of both aldehydes and ketones, which is the presence of this carbon-oxygen double bond. Remember that I don't have anything written here that indicates that I've got a carbon there, so I have this carbon-oxygen double bond, and I see that in both of these groups. I have one here and I have one here. So both aldehydes and ketones have that carbon-oxygen double bond. We also call that a carbonyl group. And what we see attached to that is, in an aldehyde, we have to have at least 1 hydrogen. So we have our 1 hydrogen here. For our ketone, what we actually see is that we have our carbonyl carbon is attached to 2 other carbon atoms. And it doesn't matter kind of where along the chain that carbonyl group is. For a ketone, it can be really positioned anywhere. So the number of carbons to the left and right of the carbonyl carbon is irrelevant as long as there are carbons on both sides. With the aldehyde, because we have to have a carbon attached to one hydrogen, what we have to see is that it has to be on the last carbon in the chain. Because if I have a carbon with 2 bonds to oxygen, that takes up 2 of my bonds. One of my bonds can be to a carbon. It could be to another hydrogen as well, but I've got it taking up 3 bonds. So if I need at least 1 bond to hydrogen, I'm going to have it on the terminal atom. If I look over here at my ketone, what I see is that when I look at this carbonyl carbon here in the middle, I see that it's got 2 bonds to oxygen, so that's 2. 3 is the third bond to a carbon atom, and 4 is a bond to a carbon atom. So we don't have any room to put in a hydrogen bond. So aldehyde and ketone both have a carbonyl group, the carbon double bonded to an oxygen. An aldehyde has at least 1 hydrogen. A ketone has 2 carbons attached to that carbonyl carbon. Any length of chain that can be there. For the aldehyde, we can also have where we have both of our atoms being hydrogen, and this is still considered an aldehyde because the defining term for an aldehyde is that it has at least 1 hydrogen, which this molecule also does. For differences in nomenclature between the two, what we see is the ending again is different for them. And for aldehydes, what we see is an AL ending. So we might see something like methanal. Note that's different than the methanol that we saw with alcohols. And for a ketone, we might see something like butanone. Okay, we're not going to see a ketone with just 1 carbon because then we're dealing with having 2 hydrogens. So we have to have at least 3 carbons in order to have a ketone. Here we actually would have 4 because we're using the but prefix. The last pair we're going to look at are the carboxylic acid and ester functional groups. And just like we saw with alcohols and ethers, aldehydes and ketones, the difference is going to be in where the hydrogen is attached and where a carbon atom is attached. And we see nothing different here. When I look first at the carboxylic acid functional group and the ester, the things that I see are the same are the double bonded oxygen and the single bonded oxygen, both to the same carbon. Okay, so that's common to both of them. What's different between them is what they are attached to. The carboxylic acid has a hydrogen attached to it, whereas the ester has a carbon group. And this could be 1 carbon or 2 carbon or 10 carbons. It doesn't matter. And so what we see is that we have a carboxyl group, and that consists of a C double bond O, OH. And then we have our ester group, which is a C double bond O, and we represent that with an R, and that just represents the R is some chain of carbon atoms. Chain of carbon. Okay, and it doesn't really matter the size. So just like we saw with the other 2 pairs, the difference lies in the hydrogen attached to this oxygen or the having a carbon attached to this oxygen. Now, when we're writing these out, we don't always want to write out and show this structure. And so what we actually use to represent this carboxylic acid group in the name is we'll say we have a COOH group. And whenever we see this part, this chunk of letters together, this chunk of elements together, we know what that this really means, carboxylic acid, but the carbon double bonded to an oxygen and single bonded to the oxygen, which has a hydrogen attached. Similar for the ester, we'll see that represented as COO R, and whatever that R group happens to be. So this shorthand, this condensed formula, means we have this. It does not mean we have a carbon attached to an oxygen bonded to an oxygen bonded to a hydrogen. So anytime you see this, know that it really means this. So that brings up an important point of condensed structures and how we show these functional groups in condensed structures. So in the next video, I'm actually going to go through some examples and give you an opportunity to practice as well how we write condensed structures. How do we show a double bond versus a triple bond when we're not showing any bonds, when we're just showing the atoms?